Hello everyone, I welcome you all to this digital classroom for the subject control systems. In the previous lecture, we solved few problems related to construction of the root locus. And today, let us solve few more problems related to the construction of root locus. You can take down this example problem. Sketch the rough nature of root locus of a certain control system whose characteristic equation is given by s cube plus 9 square plus ks plus k equal to 0, and comment on the stability. If you look into the question, sometimes the characteristic equation of the system might be given and we have to sketch the root locus. But for solving this problem, it is necessary to obtain the open loop transfer function g of s into h of s to start sketching the root locus. Now the characteristic equation is given by 1 plus g of s into h of s equal to 0. But there is a specific way to rewrite the given characteristic equation in such a form which can be compared with 1 plus g of s into h of s equal to 0 to get the open loop transfer function g of s into h of s. So we have to compare the characteristic equation with respect to the given characteristic equation, and from this comparison we have to represent in such a form that this characteristic equations should resemble of the form 1 plus g of s into h of s equal to 0. We know that gain k, which is varied from 0 to infinity, is always the numerator of g of s into h of s. That is, in the numerator of g of s into h of s, we always have the gain k, which is ranging from 0 to infinity. First, we have to collect the terms of s without k together. From the given characteristic equation, we have to collect the terms of s without k together. So in this example, we have without k these two terms, s cube plus 9s square. We have to exclude k terms and we have to consider only for without k terms. The reason is g of s into h of s will be represented in the numerator in terms of k. Then collect the terms of k together. So next step is to collect the terms of k together. So here we have k of s plus 1. I have taken k as common, so I get the third term and fourth term as k of s plus 1. Now we have to divide the entire equation by polynomial containing the terms of s without k. So now this complete characteristic equation has to be divided by the polynomial s cube plus 9 square. If you proceed these steps, this gives the form of the equation as 1 plus g of s into h of s. First, let us obtain the open loop transfer function by following this procedure. Then let us try to sketch the root locus. So we know that root locus is always symmetrical about the real axis. This is the first statement which we use to write while solving the problems related to the construction of root locus. Now let us get the value of g of s into h of s from the characteristic equation. Let us rewrite the characteristic equation as I told you, the s polynomial separately and the k term separately. Yes, we have written it s cube plus 9 square plus k of s plus 1 equal to 0. And we know the reason why we do this. We have to resemble the same standard representation of the characteristic equation as 1 plus g of s into h of s equal to 0, so that we can extract our open loop transfer function g of s into h of s. Now we know the characteristic equation is given by 1 plus g of s into h of s equal to 0. So now let us divide the entire equation by polynomial containing the terms of s without k. So let us divide this entire polynomial by s cube plus 9s square. So now the expression will be of the form s cube plus 9s square plus k of s plus 1 equal to 0, the whole divided by s cube plus 9s square. Now again you can write this expression as s cube plus 9s square divided by s cube plus 9s square plus k of s plus 1, the whole divided by s cube plus 9s square equal to 0. S cube plus 9s square divided by s cube plus 9s square, we get 1 plus k of s plus 1 divided by s cube plus 9s square. Now you can compare this with the characteristic equation 1 plus g of s into h of s equal to 0. Therefore, it is very clear that g of s into h of s will be equal to k into s plus 1 divided by s cube plus 9s square. So this procedure is mandatory. If you are given with the open loop transfer function directly g of s into h of s in the question, there is nothing to worry about solving that problem. You can construct the root locus by following the steps. Whereas if you are given with a characteristic equation of the system, it is mandatory for you to transform the characteristic equation in the form of a open loop transfer function characteristic representation 1 plus g of s into h of s equal to 0, from which you have to extract g of s into h of s following this procedure. Finally, I can write the characteristic equation as 1 plus k into s plus 1 divided by s cube plus 9s square equal to 0. Therefore, g of s into h of s will be equal to k into s plus 1 divided by s cube plus 9s square. I can again further simplify and rewrite this equation as taking s square is common from the denominator, it can be represented as k into s plus 1 divided by s square of s plus 9. Then let us follow the steps for the construction of root locus. Step 1. Step 1 is to get the general information about the number of poles and zeros as well as number of branches. Here in this example, if you look into the numerator, it is very clear that we have 1 0 at s is equal to minus 1. So number of zeros z is equal to 1. And if you look into the denominator, we have a square of s plus 9. So we have two poles at the origin, s is equal to 0, 0. And we have another pole at minus 9. So the total number of poles are 3 in this case. Therefore, p is equal to 3. As p is greater than z, the number of root locus branches n will be equal to p. Hence, n will be equal to 3 in this case. It has been written here. And at k is equal to 0, the starting point will be at s is equal to 0, 0, minus 9. This is the condition at which k equal to 0, which means that the root locus always starts with the open loop pole. So we have marked all the location of poles at 0, 0 and minus 9. And the terminating point will be at zeros. That is, we have a location of 0 at minus 1. And we know that open loop poles will be terminating at a open loop 0. In this case, as we have only 1 0, so out of these 3 poles, one of the pole will be terminating to 0 and the rest of the P minus Z branches, in this case P is 3, so 3 minus number of zeros is 1 in this case, so 3 minus 1 is 2. So two of the branches will be terminating to infinity. That is why it has been specified here as terminating point at -1, infinity, infinity. Therefore, it is very clear that we have two branches which is going to approach infinity. Moving on to the next step. Step number 2 is to identify the region of root locus. First, let us mark the location of poles and zeros in the S-plane. We have a pole at s is equal to 0 and another pole again in the same point s is equal to 0. That is multiple pole at the origin. Then we have another pole at s is equal to -9. Then let us plot the location of the 0 at s is equal to -1. And now let us find out the region of root locus. As we have multiple pole at the origin, that is two poles exactly at the same point 0. If you take any test point here in the positive real axis and if you look towards the right side and if you ask the question whether you could able to see any odd number of poles and zeros towards your right, it is no in this case. Hence, root locus does not exist in this region NRL, and we have a multiple pole at origin. And if you take a point here in this region, look towards the right side, the number of pole towards your right is 1 here. So root locus exists in this region. So it has been marked in yellow color. And now if I take a test point here in this region and if you look towards the right side, now the sum of the poles and zeros towards the right side is 2. 1, 2. Therefore, root locus does not exist in this region. I can make it as NRL. Now let me take a test point here in this place and let me look towards the right side and ask the same question. Whether you could able to see any odd number of poles and zeros towards your right. The answer is yes. We have a count of 3 here now. 1, 2, 3. That is 1 0 at -1 and 2 poles at the origin. Now the count is odd number. Therefore, root locus exists towards the left of an odd number of poles and zeros. But how long does it exist? If you are at the test point now at -9, look towards the right side. Now the count is 3. Therefore, root locus exists until this region. But immediately once you exceed this test point at s is equal to -9, and now if you inspect looking towards the right side, and if you count the number of poles and zeros towards the right side, now it becomes an even number. The count is 1, 2, 3, 4, which is an even number. Therefore, root locus does not exist towards the left of an even number of poles and zeros. Now I can mark this region as NRL. Hence, I can say that root locus exists between -1 and -9. This is the region of root locus. And as is a multiple pole location, this also I can make it as a region of root locus. Once after identifying the region of root locus, now we have to predict for the existence of breakaway or breaking point. To check for the existence of breakaway and breaking point, we should satisfy the condition. If we have two adjacently placed poles, and if it is in the region of root locus, then there exists minimum one breakaway point. Let us see whether you could able to see such cases in this example. We have a region here in which we have two adjacently placed poles and it is in the region of root locus. Therefore, minimum one breakaway point exists here, and that location also we can identify that it will be exactly at s is equal to 0. Even the location of the breakaway point we can identify in this example as we have a multiple pole at the origin. So one breakaway point exists in this example and the breakaway point location is at s is equal to 0. Moving on to the next step. Step number 3 is to calculate the angle of asymptotes. As two branches approaches to infinity, we have two asymptotes to be calculated in this example. Let us write the formula for calculation of asymptotes in which theta is given by 2q plus 1 into 180 degree divided by p minus z, where q ranges from 0, 1, 2 and so on, extended to the range of p minus z minus 1. In this case, number of poles is equal to 3 and number of 0 is equal to 1. So 3 minus 1 minus 1, 3 minus 2, we get 1. Therefore, q ranges from 0, 1 as the maximum limit is 3 minus 1 minus 1, that is 3 minus 2, which is 1. Substituting for q equal to 0, angle of asymptote theta is given by 1 into 180 degree divided by p is 3 in this case and z is 1, that is 180 degree divided by 2. Hence the first angle of asymptote is at 90 degree. Let us substitute for q as 1 for the second case. Hence theta 2 will be equal to 2 plus 1, that is 3 times of 180 degree divided by 3 minus 1, that is 2. Therefore 3 into 180 degree divided by 2. Hence theta 2 will be equal to 270 degree. Step number 4 is to calculate the centroid. Centroid is given by sigma is equal to real part of poles minus real part of zeros divided by p minus z. Let us sum up all the real part in this example. We have a pole at 0 plus 0 and we have another pole at minus 9. So 0 plus 0 minus 9 minus of, it's in the formula. And the real part of 0 is that we have a 0 at the location minus 1. So it has been written here. Let us sum up all. The whole divided by p minus z. P is 3 in this case and z is 1. 3 minus 1 is 2. Further simplification, centroid will be equal to minus 4. Now, making use of step number 3 and 4, with centroid as the center of the asymptotes, we have to plot the angle of asymptote, one at 90 degree and the other at 270 degree. So this is the S-plane and let us mark the location of poles and zeros. Multiple pole at the origin, two poles at the origin. We have a pole at minus 9, a 0 at minus 1 and the region of root locus also has been highlighted. Now let us mark the centroid exactly at minus 4. And now with the centroid as center, we can mark the angle as 90 degree, the first angle of asymptote as well as 270 degree. 90 degree exactly comes here, a vertical line, and 270 degree it will be exactly beside this. It's not necessary to use the protractor in this example as it is 90 and 270 degree. So let us extend the angle of asymptotes by dotted line, marking it as 90 degree and 270 degree with centroid as the center of the asymptote. Let us mark the centroid as minus 4 and mark the angle of asymptote 90 degree and 270 degree in the S-plane. Moving on to the next step, is to calculate the breakaway point. The characteristic equation is given by s cube plus 9s square plus ks plus k equal to 0. We know the procedure to calculate the breakaway point. The first step is to write the characteristic equation. Then we have to represent k in terms of the polynomial. So in this expression, I can write it as s cube plus 9s square plus k into s plus 1 divided by 0. So k into s plus 1 will be equal to minus s cube minus 9s square. Hence, k will be equal to minus s cube minus 9s square divided by s plus 1. Once after representing k in terms of the polynomial, then we have to differentiate k with respect to s and equate it to 0. dk by ds, and you have to equate it to 0. We have represented k here. Now we have to differentiate dk by ds. It is of the form u by v. We know the formula v du minus u dv divided by v square for dk by ds. So we have bs s plus 1. So the denominator will be of the form s plus 1 the whole square. Then v is s plus 1 into du. Differentiation of minus s cube is minus 3s square, and differentiation of minus 9s square is minus 18s. Minus of u. U in this case is minus 3s cube minus 9a square dv. Differentiation of s is 1 and 1 is 0, so I can write it as 1. This is what written here, and it has to be equated to 0. Then further simplification, taking s plus 1 the whole square towards the right, it vanishes. Therefore we get minus 3s cube minus 3s square minus 18s square minus 18s minus into minus s cube, it will be plus s cube, minus into minus 9s square, it will be plus 9s square, which is equal to 0. Minus 3s cube plus s cube will be minus 2s cube minus 3s square minus 18s square plus 9s square. Minus 18s square plus 9s square will be equal to minus 9s square. Minus 9s square minus 3s square will be 12s square. Minus 12s square. Then we have minus 18s, which is equal to 0. We can take s as common outside, and it will be of the form s into 2s square plus 12s plus 18 equal to 0. This is what written here. Now simplifying this equation, s will be equal to 0, and we can take 2 as common. It will be of the form a square plus 6s plus 9 equal to 0. Therefore now a square plus 6s plus 9 equal to 0. I can write this as a square plus 3s plus 3s plus 9 equal to 0. Yes, I can take common outside. It will be of the form s into s plus 3 plus 3. I can take a common outside, so it will be 3 into s plus 3, which is equal to 0. So I can write it as s plus 3 into s plus 3 equal to 0. So I get two roots at s is equal to minus 3, comma minus 3. And first root is at s is equal to 0. Therefore, finally you get three roots at 0, comma minus 3, comma minus 3. Now let us check for the validity of these breakaway points. We have marked the poles and zeros and the region of asymptotes, then the centroid and the angle of asymptotes. Now we have a breakaway point at s is equal to 0. This has been predicted already. Now we have to check for the validity of the breakaway point at s is equal to 0, comma minus 3, comma minus 3. We have already predicted that one breakaway point exists here at s is equal to 0. It is a valid one. And minus 3, comma minus 3, the location of the breakaway point. It is seen here, minus 3. The location of the breakaway point, the location is here, s is equal to minus 3. This is a very rare case in which prediction of the breakaway point is not identified in step number 2, whereas in this case s is equal to minus 3 becomes valid in this case due to the following reasons. As we have predicted a breakaway point exactly in this region, it is the tendency of the students to represent the movement of the branches of root locus based upon the asymptote, which is guiding at 90° and 270°, treating minus 3, comma minus 3 to be as invalid. But this leads to a wrong plot. If you look into the other side, when k is equal to 0, we have a pole at s is equal to minus 9. And when k increases, we could able to see the movement of these poles in this direction. And when k reaches infinity, it has to reach the pole. But in the meantime, we have a location of a breakaway point at s is equal to minus 3. Therefore, this branch tries to break away and follow the path of the asymptotes. So the path of the root locus which we have traced right now from breaking away from 0 is a wrong perception. So let us redraw this. So when k is equal to 0, we have the location of poles at 0, 0 and at s is equal to minus 9. And when k starts increasing, there will be a movement of these poles in this direction. And here the pole, multiple pole at the origin tries to break away at s is equal to 0, and it tries to follow the path of the asymptotes moving in this direction. And at one particular value of k, all these three branches meet at a single point, and this point indicates a location of triple roots. So for in all the examples, we have discussed only with respect to a intersection point of two poles, whereas in this case, it leads to an intersection of triple poles. One moving from minus 9, one moving from one end of the branch for s is equal to 0, another moving from other end of the branch at s is equal to 0. And this indicates the location of triple roots intersecting at a single point for a particular value of k. And this is for the particular case at which we have obtained the breakaway and breaking point at minus 3, comma minus 3. As the branches are moving away from real axis, entering the complex plane, and as it is trying to enter into the real axis from the complex plane, you can treat the location of s is equal to minus 3 as breaking point. Now, once if you keep on increasing the value of k beyond this range, so exactly at this point at which you could able to see triple roots, these branches try to break away again at the same location at s is equal to minus 3, following the path of the asymptotes reaching infinity. This is a very rare case and it is the most important repeated university question. You can make a note of it. So this is the actual rough plot of the root locus. So we have few more steps to be discussed and let us finalize with the plot at the end of this session. Moving on to the next step is to find the intersection of the root locus with imaginary axis. If you inspect the previous case, as we have an asymptote at 90 degree and 270 degree, there is no possible for the pole at the origin or the pole which is located at minus 9, the branches will not try to intersect on the imaginary axis, as we don't have an asymptote which is guiding the root locus towards the imaginary axis or towards the right half of the S-plane. This is based on prediction. Let us justify this by following the steps. The first step is to write the characteristic equation which is given by s cube plus 9s square plus ks plus k equal to 0. The first step is to generate the route array. So let us write the s terms and fill up the first two rows by filling the coefficient of s cube as 1, then the coefficient of s square as 9, then the coefficient of s is k and the constant k. Once after filling the first two rows, we know to fill up the third row first element, making use of the formula 9 into k minus 1 into k divided by 9. Hence, we get the expression as 8k divided by 9. Then the third row second element will be equal to 0, as we are filling the rest of the element to be 0. Then the fourth row first element is given by 8k by 9 into k minus 9 into 0 divided by 8k by 9. 8k by 9 in the numerator and denominator will get cancelled out. Therefore, for the s to the power 0 row, the first element will be equal to k. Once after generating the route array, we have to interpret with the route array, looking into the first column, and we have to determine the range of k as well as k margin. So let us equate s to the power 0 row as k greater than 0. That is, for a system to be stable, all the elements in the first column of the route array should be positive. That is, there should not be any sign changes. So this condition is k greater than 0. Now if you look into the s to the power 1 row, 8k divided by 9 will be equal to 0. Therefore, k will be equal to 0 if you equate s to the power 1 row. So the marginal value of k, which makes the row of s to the power 1 as a row of 0, this s to the power 1 row becomes complete 0 row when k equal to 0. But a system cannot work with k equal to 0, which means that this clearly indicates that there is no intersection of roots on the imaginary axis. And this is how you have to find the value of k. Step number 7 is to calculate the angle of departure and angle of arrival, which is not applicable in this example as we don't have any complex conjugate pole or zeros in this example. So moving on to the next step, let us plot the final sketch of the root locus, location of poles and zeros, the centroid at -4, the angle of asymptote at 90 and 270 degree, then the breakaway point at s is equal to 0, and we have a breakaway point at -3 also. So as we have represented the rough sketch, let us finalize with the plot now. From the breakaway point, when k increases from 0 to infinity, the branches try to break away and break in at s is equal to minus 3, and at this location exactly, now all these poles try to meet at a single point for a particular value of k, and when k is increased further, it tries to break away again at the same location as is equal to minus 3, and these branches try to reach infinity. And this shows the clear movement of these poles with the direction of the movement of the poles. The final sketch with the direction of the root movements as k increases from 0 to infinity is clearly shown here. So let me repeat once again. When k equal to 0, we could able to see the location of poles and zeros, that is the starting point of the poles and zeros will be exactly at s is equal to 0, 0, minus 9. When k increases, we could able to see the movement of these poles in the region of root locus, and they try to intersect at a single point, which indicates the location of triple roots for the solution of the breakaway point at s is equal to minus 3. And then if you try to increase k further, these three poles, which is located at the point minus 3, tries to break away, and one of the pole will try to reach 0 when k reaches infinity, and the rest of the two poles will try to reach infinity, breaking away again exactly at s is equal to minus 3. And this shows the clear picture about the movement of these poles for k ranging from 0 to infinity. In the next lecture, let us solve few more example problems related to the construction of root locus. Thank you.